Hello again, and welcome to the second of 5 videos on a short introduction to radioactivity. This is the second video, and this time I'm actually going to talk about what is radioactivity, having talked about basic nuclear physics last time. Okay, so what is radioactivity? In short, if you have a look at the slide, radioactivity is the spontaneous decay of unstable parent nuclei into more stable daughter nuclei through the emission of ionizing radiation. Okay? So the basic idea here is that some atomic nuclei are inherently unstable, and what they want to do is they want to achieve a more stable configuration. The way that they do this is they emit a little bit of radiation, and this allows them to change into a different chemical element which hopefully is more stable. So sometimes this can be a short process, and sometimes it can be a long process. Okay, so if you have a look at the slide, here is an example of a radioactive decay chain for lead-212. So you can see from the notation there that lead is represented by Pb, which I believe is Latin for plumbum, and this contains 212 nucleons in total in the atomic nucleus, 82 of which are protons. Now this is a very unstable configuration, and what lead wants to do is it wants to achieve something that's more stable, so it decays to bismuth-212, which contains 212 nucleons in the atomic nucleus, 83 of which are protons. So this is different from lead, which has only 82 protons. I will explain, or the aim of this video is to give you enough information to understand this particular decay chain, which should help you understand the process of radioactive decay more generally. Okay, now one thing that I'd like to talk about now is that radioactivity is a random process. Okay, so we can't predict when any given atom, which is unstable, is going to undergo radioactive decay and turn into a different, more stable atom. If you have a look at the slide, there's a graph that attempts to represent this using a concept called the half-life. Okay, so the half-life is the time taken for half of the nuclei in any given sample of a particular chemical element, radioactive chemical element, to decay. And this we try and capture with the graph there. So if you look at time equals 0, the time units here are in half-lives, you can see that all of the dots in the sample are black. So here all of the elements are brand new, nothing has decayed. After one half-life, you can see that 10 of the 20 dots have decayed. They've gone from black to red, so they've become something more stable as a daughter atom. But there are still 10 left. After a second half-life, when we get to T equals 2, we can see that of the remaining 10 that hadn't decayed at the first step, an additional 5 have now decayed. Okay, so we've decreased the number of parent atoms there by 3/4. We've only got 5 parents left that can decay at the next time step. So this captures very nicely the idea of the radioactive half-life, which is a really important concept and can give us some useful information about different radioactive elements. Okay, so here is an example that I have tried to prepare to explicate some of the things that we can learn using the half-life. So here, as in the last slide, parent atoms that are radioactive are represented by black, and daughter atoms that are stable are represented by red. So this is a very simple decay chain. Everything just goes from parent to daughter, nothing else included. Okay, so suppose we have 2 samples of the same radioactive material. Here we have sample A, which is brand new, and we have sample B, which has been left hanging around for a little bit longer. So sample B is 1 half-life old, which means that half of the original sample has already decayed from parent to daughter. So which of these samples is more radioactive? A different way of asking this question is how many nuclei will decay in the next half-life? Okay, So looking at sample A, because it's brand new, none of the parent atoms had yet decayed. Over the course of one half-life, half of that sample will decay. So here that's represented by 2 blocks that will have decayed. For sample B, because it's already 1/2 older, after another 1 half-life old, after another half-life it will be 2 half-lives old, which means that 3/4 of the original sample will have decayed. So over the time period from the end of the first half-life to the end of the second half-life, sample A will have produced 2 units of radioactivity, whereas sample B will have produced only 1 unit of radioactivity. Okay, so this means that sample A is more radioactive at that time. So what is the lesson here? The lesson is that over time, a given sample of radioactive material will become less radioactive as more and more and more of the parent atoms have decayed into more stable daughter atoms. Okay, so this is a useful thing to know. For example, when we think about the fabrication of a dirty bomb, we're most concerned about brand new radioactive sources, which are incredibly radioactive, whereas a source that's been left around for 20 years will have decayed significantly and will contain only a small fraction of the radioactivity it originally contained 20 years earlier. Okay, what else can we learn using the half-life? If you have a look at this slide, I have another example that illustrates something that the half-life can tell us. So this is the same format as before. Parent atoms are in black and daughter atoms are in red. Okay, so suppose we have 2 samples of different radioactive materials this time. Sample C on the left has quite a short half-life compared to sample D, whose half-life is twice as long as sample C. So again, the question is, which is more radioactive after 1 half-life? Okay, so if we look at sample D, it has 1 half-life, or its half-life is represented by T half, I should say. So after that length of time, half of the sample will have decayed. However, when we look at sample C, we see that its half-life is only half the time compared to sample D. This means that after 2 of those periods, 3/4 of that sample will have decayed. And therefore sample C is more radioactive over 1 half-life compared to sample D. What is the lesson of this complicated example? All things being equal, all other things being equal, a shorter half-life indicates a more radioactive element. So something like uranium, which has a half-life of 4.5 billion years, is much less radioactive than something like cobalt-60, which has a half-life of about 5 and a bit years. So we're much more concerned from a radiological protection point of view about radioactive materials that have very short half-lives, because they produce much more radioactivity and are therefore much more of a threat to human health.